Okay, I'm back. We had to take a little break for some vacuuming in the classroom. So now we're back to some, so we've looked at the limitations for a simple, or a pendulum. Simple pendulum meaning that it undergoes simple harmonic motion, but that only happens if the angle, if the maximum angle of displacement is about 10 degrees or less. So our first concept question. We have two pendula. Oh, look, it looks like that's the plural, according to at least our textbook authors. So two pendula have the same length, but different masses. How do their periods compare? We just talked about it. So it's really surprising, but the mass attached to the end of the string does not influence the period of the pendulum. The follow-up question is, what happens if the amplitude is doubled? And again, surprisingly, amplitude does not affect the period. So the only things that affect the period are the length of the string and acceleration due to gravity. Two pendula have different lengths. One has length L and the other has length 4L. How do their periods compare? So the pendulum with length 4L has a period that's twice that of the pendulum with length L. And it's twice as large because, of course, it's square root of L over G, so 4 times the length gets square rooted to be double the period. This is one that I have a question about. So a grandfather clock has a weight at the bottom of the pendulum that can be moved up or down. If the clock is running slow, what should you do to adjust the time properly? So my grandfather gave me his clock. It was his grandfather's clock, I think. And on the inside of the pendulum part, which is removable, there's a little screw with a nut, and you can adjust the nut up or down to make fine adjustments in the period of the clock. Okay. So my clock used to be in Lacey Olympia, or at least it was most recently in Lacey Olympia. No, that's not true, actually. It was most recently in Oregon City, Oregon, but it doesn't really matter, West Coast, right? And down at sea level. And now we're here up in Utah at a higher elevation, so nominally further from the center of the earth. So the clock runs slow. So if the clock runs slow, what could you do to adjust the time? Should you move the weight up? Should you move the weight down? Will moving the weight not matter? Or should you call the repairman? At this point in my life, I think I want to call the repairman because there's worse things going on with the clock. But if the only thing that's wrong with it is that it's running slow, what should you do? So you should move the weight up. If the period is too long, so if it's running slow, 1 second is a little bit longer than 1 second, right? It's ticking off something that's too long, longer than 1 second. So we need to make the period shorter. And to do that, we need to make the length shorter. So we need to move the weight up to effectively shorten the pendulum, right? By moving the weight up, we move the center of mass of the weight a little bit closer to the axis of rotation, and that effectively shortens the length. So my personal story is that I tried this and I just screwed the clock up even worse. So now I need to call the repairman or find a repairman for an antique clock. So a little knowledge is not necessarily a good thing. Okay, so as long as the cord can be considered massless and the amplitude is small, the period does not depend on the mass. We see here a picture of a cathedral. I can't actually identify this cathedral. I think it's a cathedral. It looks like a religious institution of some type. In any case, Galileo is credited with this discovery, I would guess, I would call it a discovery, of the relationship between period and pendulum length, and the fact that pendulum period does not depend on anything else. The sort of myth, it's not quite a myth, what's the word? The tall tale is that he was sitting in mass and watching the chandeliers swing to and fro. If you sit in mass like I sit in mass, You do a lot of watching of chandeliers and other things. And for those of you who don't know, Mass is the religious ceremony attended by Catholics, people who follow the Catholic religion. And so he was watching the chandeliers swing, and he noticed that the chandeliers of the same length all swung at the same rate, and chandeliers of different lengths swung at different rates, regardless of like what was attached to the chandelier. So there you go. It's like an urban legend, right? A legend, that's the word. Okay, so now consider a pendulum that has a period of T on Earth, and you pick that pendulum up and you take it to the moon. How does the new period of the pendulum compare to the old period? Or is it the same? Does it not change? What do we know about the moon compared to Earth? So you should answer that the period increases because on the moon there is a weaker gravity, and acceleration due to gravity is smaller. So square root of L over G gets, if G gets smaller, square root of L over G gets larger. And then what would you do to return the pendulum to its original period? So you've got a smaller G, so would you make the pendulum longer or would you make it shorter? That's a good question. All right, so here are a couple of example problems. A pendulum has a period of 1.85 seconds on Earth. What is its period on Mars, where acceleration due to gravity is about 0.37 of that on Earth? So we're just, for these problems, working with period is equal to 2 pi times the square root of L over G. So knowing that the period is 1.85 seconds on Earth means we know the period value. I just want to make sure that it's square root, or it's 2 pi times square root of L over G, because, yes, okay, because I never now trust myself with whether it's 1 over 2 pi or 2 pi. Okay, so 2 pi, square root of L over G, right? So we know the period, we know G on Earth is 9.8. This allows us to find the length of the pendulum. Then we take this pendulum to Mars, we have a new G, we plug in to find the new period. I suppose we could probably do a ratio, but it's Friday and it's almost 5, and this is how we're going to do it. So we have period squared over 4 pi squared, right? So I squared both sides, moved that over, is equal to L over G. So L is equal to period squared G over 4 pi squared. Okay, so the period is 1.85 seconds, and G is 9.8. Oh, I suppose you can't actually see what's going on the calculator there. Oof. Oh, we have some glare. I don't see how I can fix that. I can kind of tip it. Okay, what am I doing now? I need to divide by 4 pi squared. Where's the squared button? There we go. All right, so the length is 0.84959. 84959, so we'll call it 8496 meters. I've thrown in an extra sig fig there just for kicks. And then we want to now find the period when it's on Mars, where we have the known length, and instead of 9.8, we have 0.37 times 9.8. I've dropped the units just out of laziness, but I'm confirming. I mean, this is meters per second squared, this is unitless, we're good. Okay, so now we calculate the new period. Oh, and actually what I think I want to do is just use that answer, divide by 0.37 times 9.8. And then I need to take the square root of L over G. So take the square root of the answer and then multiply that puppy by 2 pi. Okay, so I have a new period of 3.04 seconds. So on Earth, where gravity is stronger, 1.85 seconds. On Mars, where gravity is weaker, 0.37 seconds. Oh yeah, I totally see. This should have been a ratio. Could have, should have, would have. If you can see how to make this a ratio, hooray for you. You don't have to solve for the length because the length is the same for both. If not, you can just plug through like I have and find the length of the pendulum. But as I'm saying, it's 4:50, it's Friday, and we're just going to go with it. All right, so my next example, again, we're just dealing with pendulums and that new equation for pendulum period or for pendulum frequency. So how long must a simple pendulum be if it's to make exactly one swing per second? So one swing per second, they're saying that is one complete oscillation takes exactly 2 seconds. That's good to note. So they're saying one swing. So from side to side is 1 second. But a period means from starting point back to starting point. So that hint is very helpful because that means the period needs to be 2 seconds. So 2 seconds is equal to 2 pi times the square root of L over G. And again, we know G on Earth is 9.8 meters per second squared. So 2 seconds over 2 pi is the square root of L over G. We got to square both sides, so it's going to be, oh, I can cancel that out, right? So it's going to be 1 over pi squared is equal to L over G. So L should be equal to G over pi squared. And let's find out what that is. So G over pi squared. And I guess we're about to find out the length of my grandpa's clock. There. 0.992, whatever. Let's do 3 sig figs, right? 0.993 meters. So almost a meter. My grandfather clock is not actually a grandfather clock. It's just like a wall clock. And I don't think that the pendulum is 0.993 meters. It's about half a meter. So this would be tick tock, right? 1 second between. I'm betting that my clock goes tick tock, right? So that it's one complete swing each second or something. I don't know. I guess I should measure the clock pendulum length and get back to you on that. All right, so damped motion. So when an object undergoes simple harmonic motion in the presence of friction or drag or similar, that harmonic motion is going to change over time, and it's going to be what you see when you watch a pendulum swinging. It swings from side to side, but the motion gets smaller and smaller as time goes on until the pendulum is hanging back at equilibrium position. So if the damping is small, if that frictional force is small compared to the restoring force on the pendulum or compared to the restoring force due to the spring, then we treat the damping as an envelope. The envelope causes the amplitude of the oscillation to get smaller and smaller, but it doesn't change the frequency and or the period. So the damping affects the amplitude, but not the frequency or period. And it causes the oscillation to sort of squeeze between this envelope, and the envelope is described by the frictional forces, and it depends on the frictional forces. The dependence and sort of size and shape of this envelope is beyond the scope of this course. So we're just focusing on the idea. So after a pendulum starts swinging, its amplitude gradually decreases with time because of friction. What happens to the period of the pendulum during this time? According to my previous statement, the period doesn't depend on amplitude, and it's the amplitude that gets smaller because of the friction, so the period does not change. What happens to the energy of the pendulum is a good question. If amplitude decreases, and we could model this after a mass on a spring where we know that the maximum energy is equal to 1/2 k times amplitude squared, we can expect something similar for a pendulum. If it's the amplitude that's decreasing, it doesn't really matter about the time, the energy is also decreasing. Or I should say the mechanical energy is decreasing, right? That combination of kinetic plus spring potential or the combination of kinetic plus gravitational potential is decreasing as the mechanical energy is being transformed into heat due to the friction. So we have small damping forces or a small frictional force compared to the restoring force, and then we have large frictional forces compared to the restoring force. If that damping force is large, we really don't see anything that looks like simple harmonic motion. we do not see a sine or cosine wave. In line A of this graph, we have underdamping. So the object is sort of allowed by friction to oscillate a few times before the oscillator comes to rest. It's almost like the envelope here, but where the envelope is super steep. B is critical damping. So that's the way that's like sort of the perfect amount of friction, where the thing doesn't even undergo a single oscillation. It just kind of curves down to x equals 0 in the shortest time possible. And then over damping is there's so much friction that the object sort of floats to a stop, but takes longer than critical damping. It takes a long time to get back to equilibrium. And again, the mathematics describing these things is beyond the scope of this course. We're just going to be familiar with underdamping, critical damping, and overdamping compared to sort of damped harmonic motion, where the oscillations fit within that envelope, but there's no change to the timiness of the oscillation. So systems where damping is unwanted, such as clocks and watches, we try to eliminate friction. We try to provide ways for the oscillation to like regain mechanical energy, either with a battery or in my grandfather's clock, I have to wind it up every week or so if I remember. But then there are systems in which we don't want, or we do rather want damping, and we might like to have critical damping so that the object does not oscillate. And so shock absorbers and earthquake protection for buildings are examples where we're trying to achieve critical damping so that there is minimal oscillation after a disturbance, right? After you go over a bump or after an earthquake wave passes the building. So kind of the opposite of damping is forced oscillations. We'll look more at forced oscillations and resonance when we look at waves and music. But in general, a forced vibration occurs when there's a periodic driving force. So the force itself is periodic, and that force may or may not have the same period as the natural frequency of the system. So you've got a mass on a spring where the spring is causing the restoring force, and the natural frequency is determined by the mass and by the strength of the spring. And then to that, you attach some kind of variable force, right? You've got some kind of force that pushes and pulls and pushes and pulls in a periodic way. And that push-pull outside of the system may or may not be at the same frequency as is determined by the sort of structure of the system. In the case where the driving frequency, so the frequency of the outside push or pull, is equal to the frequency determined by K and M, then the amplitude becomes large, and this is called resonance. So the frequency of the external push-pull matches the frequency that this block and spring oscillate at, whether there's an outside force or not. And when that's the case, you see resonance. So here you see a graph of frequency versus amplitude of the oscillating system. So this would be the frequency of the external push or pull, the driving frequency. So this push and pull of the hand of the machine, whatever it is that's pushing and pulling on the spring. So as you increase that frequency, the amplitude of the oscillation increases to a peak. That peak occurs when the frequency of the push-pull external sort of driving force equals the 2 pi square root of K over M, or whatever it is, for the mass in the spring. And then as you continue to increase the frequency of the driving force, the amplitude of oscillation actually decreases again. So if there's very little damping, you get a very sharp peak at the resonant frequency. And if there's damping, if there's a lot of friction, you get a smaller peak, but you still get a peak. And so just like damping, resonance can be wanted or unwanted. In musical instruments, you're really trying to achieve resonance. So like I said, we'll talk some more about that after we've discussed waves. But producing musical sounds is all about achieving resonance. I play the flute, so that's what I think of the most. So you're trying to have your flute body resonate, and you're trying to create a standing wave of air inside of that instrument's body. And the resonant frequency you are trying to play is the frequency of the note you're trying to play. I don't know that that makes sense, but we'll make sure it makes sense later, because it is now 5:01 on Friday afternoon. So if you're sitting on a swing, this actually, I couldn't find any example questions about resonance in this section of the textbook. And like I said, we're coming back to it anyway. So imagine you're sitting on a swing and a friend gives you a push and you start swinging with period T1. What if instead you were standing on the swing rather than sitting? And when you're given the same push, you start swinging with a different period. How does the period of your swing when you're sitting compare to the period of your swing when you're standing? You might think about my grandfather clock example. If you answered B, you're correct. So by standing, you're essentially raising the center of mass of the system, which is the same as making a shorter pendulum length, and so the period decreases. I was just checking myself to make sure that's true. Yeah, period decreases. Just like when I screwed the nut and made the nut go higher up on my grandfather's clock and made the period shorter, but it's still broken. So this is the end of the oscillations lecture. We're finished with simple harmonic motion and oscillations for now. You have an additional homework assignment on Canvas. I think I've called it, let's see what I've called it. I called it Chapter 11 Problems 2. You need to complete that and be ready to discuss. I was going to say next Friday, but I'm not going to see you next Friday. So you have a little leeway here. You need to get this done. And I will see you again, unless you're in the robotics team, I will see you again on March 6th when we begin talking about waves. On Friday, the 1st of March, when I will be at the FRC competition, I'm going to give you guys a practice test to work on. And then all of you robotics people, well, you 3 or 4 robotics people, I don't know what, maybe I'll bring the practice test to the competition for you or something scary like that. In any case, I hope you have a nice weekend. I'll be at school. You can come check in and ask me questions. And I'm always supposed to say, please like and subscribe and comment. I think that's what you're supposed to say, but I don't really want your comments. Well, yeah, I do. I want to know how this is working for you. Have a nice weekend, and I'll see you later. Goodbye, AP students.